In this video, we're going to do day 2 of the limits discussion from 1.4. So we're going to work with the very top of the page of notes, and it says using algebraic manipulations to compute limits. So if we were to just plug in x equals 4, what's going to happen is your denominator is going to go immediately to 0, which will give us an undefined. So this is what we call, when we graph it, and we see we have a hole. So when we graph it, which is here, we have a hole right there where x is 4. So remember, this is called a removable discontinuity. So when you have a removable discontinuity, you can factor and cancel and get your limit. So the limit is what your function would have approached if the hole was not there. So I illustrated factoring and canceling, and from Algebra 2 we learned that if you're able to factor and cancel, you do not have a horizontal asymptote, you don't have a vertical asymptote at x equals 4, but rather you have a hole. So once we factor and cancel, then try to put in the 4. When you put in the 4 at that point, you get a limit of 8. So let's try another one. What if I said I wanted to find the limit as x goes to 5, and here's my function, x squared minus 25 over x minus 5. Alright, if I plug in a 5, I can see my denominator is going to go directly to 0 and my function will be undefined. So let's factor first, cancel where we can, and then try to take the limit. So I have the same situation, but now I'm going to factor my numerator into x plus 5 times x minus 5. And I see that my x minus 5's will cancel. Once they cancel, take your limit, and you'll see if you plug a 5 in for the x plus 5 equals 10, and we had another removable discontinuity. So hopefully you understand that. Sometimes you may try to factor, but you can't cancel, or you can't completely cancel what you wanted to cancel, and therefore you still have no limit. The limit does not exist. So don't think just because you're factoring, you're going to actually get a limit. Sometimes you still don't get one. But first, before you throw in the towel, factor first, cancel where you can, and then try to take the limit one more time. Okay, so that's your first algebraic manipulation. We're going to do another one, and that will be on the next page, dealing with radicals, and we're going to work with conjugate pairs. Alright, in the next example, in the bottom of that first page of day 2 of the notes, it says dealing with radicals. So when you see a radical in the numerator, you know that there's going to be something that you can do to perhaps be able to find the limit. When it first appears, plugging in the value of 0 into my denominator results in no limit. So before you throw in the towel, you're going to do an algebraic manipulation called working with conjugate pairs. So right here, I'm going to circle, here is my function. Looking at my numerator, to get the conjugate pair, you're going to write exactly what you see in your numerator and change the operation between the two terms. Then you're going to put it over itself, because this whole expression is just a fancy 1, and that's why you're allowed to do it. Alright, so I see I have a radical. I think, oh, let's do the conjugate pair method to see if I can eliminate having that x in the denominator. So I've told you how you find it. Now let me just get rid of some of those marks so that we can see what we're doing. Okay, so next thing. Now we're going to look at the graph too. So if you look at the graph and you analyze it, you can see that you have a hole where x is 0. Now when you graph it, you're not going to see the hole. But if you look at your table, you're going to get an error where x is 0. If you look at your graph and try to evaluate the function for x is 0, your graphing calculator will not give you a value. That's your tip-off that you have a hole. Okay, so we have worked with the conjugate pairs. Now, a couple of things. When working with conjugate pairs, you don't have to do all the messy math. What you can do is look for a pattern. So this is my pattern. If I say the radical x plus 4 is my A term, and the 2 is my B, and again, this is my A, and this is my B, and there's a subtraction here and an addition here. Over here, when I FOIL it, A minus B times A plus B, I will do all the steps. And doing all the steps gets me A squared minus BA plus BA minus B squared. These terms will drop out, and I basically have A squared minus B squared. So looking at my numerator, what's my A? My A is radical x plus 4. If I square it, then I would just have x plus 4. Looking at my numerator again, what's my B? Well, my B is 2. If I square that, I get 4. So A squared minus B squared will be x plus 4 minus 4. And that is my next step right here. The denominator is going to come along and be placed next to the original denominator of x. So cancel what you can, and the 4's cancel because they are opposite signs. The x over x cancels and becomes a 1. So in my denominator, I'm left with x plus 4 plus 2. Now I'm ready to take the limit, because once I plug in a 0 for my x, I end up with 1 over radical 4 plus 2. Taking just the principal root, I end up with 1 over 2 plus 2, which results in a value of 1/4. 1/4 is where the function would have hit the y-axis had there not been a hole there. So, things to take away from this. I've recognized a hole. This particular function does not have a value where x is 0 because there is indeed a hole there on the function. It does have a limit because from the left and from the right, as your x approaches 0, you are converging on the y value on 1/4, and 1/4 is indeed your limit. Okay, on the top page of this page of notes where it says limits and the derivative, this is just a review once again as analyzing the limit as going from the slope of a secant line to the slope of a tangent line. So I've written out, just for completeness, here is your difference quotient. Without having an actual equation, I really can only simplify it to this. So right now, from this point forward, if you prefer to use this as your difference quotient, you may. So the difference between what I generally use, which is this one, and this is that the x's in the denominator have already been canceled. So this is your difference quotient. Over here, the graph talks about your x plus h, your x and your x plus h, your f of x and your f of x plus h, and how in the limit, as this difference right here, which would be h, goes to 0, your function goes from f of x plus h to f of x, and the slope ends up being that of the tangent line drawn to the curve at the value x. So that's what we're doing. I want you always to keep that in mind so you have an idea of the big picture. Don't get lost in all the details. Keep the big picture in mind. This is what a limit is. So in the next page, we're going to go through the limit as h goes to 0 of x squared, and then also the limit as h goes to 0 of x cubed, which you've seen before and which you've actually done, but I'm going to do it one more time for you. Okay, here we're going to have f of x equal to x squared, and we're going to establish the difference quotient. So you can see in these steps right here, in step 1 and step 2, the notation that you see here and here and here, all is this. And you want to write that every single time. Okay, this notation is critically important. Memorize it, know how you write it. It is f prime of x equals the limit as h goes to 0. Because remember, f prime of x is your slope of the tangent line. As h goes to 0, your problem actually becomes the f prime of x, and therefore you don't have to write as h goes to 0 once you actually plug in the 0. Okay, so these steps you should be okay with. Notice I'm doing nice neat algebra, and then this last step here, when those h canceled, they became a 1. When the other terms in step 2 canceled, so right over here, those became zeros because they were opposite sign and they were all in the numerator. Then we go down to step 3. In step 3, what you're going to see is no limit as h goes to 0. Why is that the case? Well, look right here. Do you see how you've already plugged in for the 0? So you're actually taking the limit now. And here is your first derivative. Now, if you would have done the power rule, we would have said f of x equals x squared, and therefore using the power rule, f prime of x equals 2x to the first, and these are equivalent. Now remember, I told you that what's going to happen pretty soon is you will not be able to use the power rule to get your answer, so your limit will have to be obtained by using your correct steps to get the limit through the difference quotient. Alright, that's what we're practicing these steps so that we're nice and consistent and we can get an answer. So let's look at the x cubed one next. Alright, here's our x cubed problem, and again, I'm taking the limit as h goes to 0, so be very careful about all the notation. These 3 steps have the same notation. Once we clean everything up, and we're actually able to put 0 in for h without having it be in the denominator, we can then take the limit. So here, I don't say I'm taking the limit because I'm actually plugging in the 0 for every single h value. And my answer ends up being f prime of x equals x squared. So again, for this one, I could have gotten that same answer by just simply using the power rule, which I know you think is infinitely easier, and it is. But we can't always do it that way, so this technique is very, very important. Alright, there's my power rule answer, here's my limit answer, and once again, they match. Alright, we're going to go on to the next page of notes. Alright, there's a lot of writing on this page, so I think I'm going to do it just in quarters. So here's the first problem, and you should be already able to do this problem. So taking limits very carefully, we're going to use good notation, and wherever I have an x, I'm going to put an x plus h for the first term. So that is right here. Then I'm going to subtract away using parentheses the original function, and then here's my denominator as usual. Here, watching all your notation and distributing your operations appropriately, you get this for a numerator. I'm going to cancel, so let's go ahead and I'll do the actual canceling on here. So if I cancel, I see the 10, and this 10 can cancel. I see the negative x squared cancels the positive x squared, and that's all I can cancel in the numerator. And then in the denominator, I can cancel the x and the other x because they have opposite signs. My third step, I factor out my h, and I'm left with a negative 2x minus h. The h's then cancel and become a 1. And at this point, in this step of the problem, I'm going to actually plug in a 0 for my h, so I'm no longer using the limit notation. and my f prime of x equals negative 2x minus 0, which I can then simply state as f prime of x equals negative 2x. They ask us in this problem to find f prime of 3. So when I find f prime of 3, what I'm going to do is just put a 3 wherever I have an x, and my f prime of 3 ends up equaling negative 6. Now I could have also done this one using the power rule. So if my f of x equaled 10 minus x squared, using the power rule I would have gotten f prime of x equals, the derivative of a constant is just 0, and then you have your subtraction sign, and then you take the power rule and you're left with that. And then just like I did in the last step in the other problem, plug in your x value and you have a negative 6. Now let's think about what that negative 6 means. That's telling me that my function f of x equals 10 minus x squared, if I draw a tangent line to that curve at x is 3, it should have a slope of negative 6. So think about that. Make sure you understand what that means. And we're going to go forward and do other problems that are going to take a lot more algebraic manipulations. Okay, for problem B, if I have a function f of x equals 1 over 3x minus 2, in order to take the limit of that as h goes to 0, my difference quotient is going to look like this in the numerator. So notice how messy this is getting down here when I put an h next to the x. My denominator, x plus h minus x, doesn't get messy, but all of a sudden I have a double-decker fraction. So if I had, let's just think about this, 1/3 minus 1/4. So I'm just looking at the numerator of my limit and thinking of it in terms of what would I do if I had that, because I know I have to combine those two fractions. Wouldn't I have multiplied the 1/3 by 4 over 4 and the 1/4 by 3 over 3, and that would have given me 4 minus 3 over 12, which would have been 1/12 for that fraction. So this messy fraction, which I can combine, that's two fractions, really is equivalent to this one fraction, and that's my goal for my difference quotient. So look at my next step. My next step is going to be right here, and look what I've done. I've taken the denominator of the second term and put it over itself and multiply it by the first term, and then I have my subtraction again, and I've taken my denominator of my first term, put it over itself, and multiplied it by my second term, which is exactly what I did in this simple algebraic, or simple, I guess, numerical equivalent, demonstrating how to combine two fractions using common denominators. So my third step, and you may have to think about all of this a little bit because it is just basic math, but when you do it with all these x and h terms, it looks a lot more intimidating. Don't let it intimidate you. Work neatly. Look what I've done and see if you can imitate it. My next term, I have multiplied all the numerators of the numerator and combined all the terms into one long piece. I haven't canceled anything yet. So that whole top is my new numerator. Then I have a denominator that consists of my new common denominator, which is the product of the initial first denominators, times the h. Now this is worth talking about as well, so let's do something over here which is going to help clarify why the h went where it did. Let's just say for our example I had 1/12 divided by h. If I had that, isn't that really 1/12 divided by h, which is equivalent to 1/12 times 1 over h, which equals 1 times 12 over h. So what that means is that the h right here is equivalent to the h right here. It was down below over here, and I would have still had a double-decker fraction. It would have had 3 pieces. By putting it next to the other long term right here, I eliminate the double-decker nature of my fraction, and I have a simpler fraction to work with. Okay, now what I'm going to do is I'm going to actually do the canceling in red so you can see what I've done. And so in this term right here, I see that my 3x in my numerator cancels with my other 3x. My 2 cancels my 2. And I'm left with my negative 3h, moving down to this step now, and then everything in the denominator stays the same. Now at this point, you may cancel these h's, these and only those h's. And so I am ready to take the limit. So taking the limit, I eliminate the limit as h goes to 0 notation, and I instead put a 0 wherever I had an h. And so since I have 3x minus 2 times another basic 3x minus 2 once I take account of that 0, my denominator just becomes 3x minus 2 squared. So negative 3 is my numerator, 3x minus 2 squared, right over here, is my denominator. They then ask me to evaluate this slope where x is 3. And I plug in a 3 wherever I have an x, and I end up getting negative 3 over 49. Negative 3 over 49 is the slope of the tangent line drawn to the function 1 over 3x minus 2 at the x value of 3. Keep going back and reminding yourself what it is you are doing and what each piece means. So you may want to go through and practice that again to make sure that you can get what I've gotten. And then on the next page we'll start doing the bottom half of this page of notes. Okay, in 2b of this page of notes, what I'm looking at, 2a, excuse me, on this page of notes, so the bottom of the previous page, I'm now going to find the limit of f of x equals 1 over 3x as h goes to 0 using the difference quotient. So here I can't use the power rule, so I'm going to hope that my technique gets me the correct answer. So what I see is I have the same situation I had kind of diagonally above, where I have a lot of messy stuff in the denominator. So again, just to give you another example, if I had 1/5 minus 1/6, I would have multiplied by 6 over 6 on the left and 5 over 5 on the right. That would have gotten me 6 minus 5 over 30, which would have reduced to 1 over 30. So I'm doing the same thing when I do this kind of multiplication. You're allowed to do this because you're really not changing the value, you're just changing how something looks. So 1/5 minus 1/6 is the same as 1 over 30, okay, which is the same as 6 over 30 minus 5 over 30, which is a lot easier to deal with because you have a common denominator. So I am creating my common denominator, and then I'm very carefully distributing my negative so that I get to this step. So when I get to this third step, what's happening is I kind of have a messy denominator. And we talked about combining this h in the bottom and the reason why I can do that. So I'll go through that again. So let me just erase what I had here. Oop. And then I'm going to have to do something else here. So let me just color this in again. And what I'm going to do is talk about the h in another example in case you needed some reinforcement. So, for example, if you had 1 over 30 divided by h, that's just like 1 over 30 divided by h, and you don't really divide fractions. You multiply by the reciprocal, and that's why let me just do this, you can write that as 1 over 30 times h. So I've basically taken the two denominators and combined them into one denominator. And that's exactly what's happening here and here with my h. So this little h that was right over there ended up being moved up to the other term. So here in this, let me change my color so you can see what I'm doing. Okay, so in this step right here, I'm now going to start canceling some things out. So what can cancel? So my 3x can cancel my negative 3x, and that leaves me with negative 3h over h, and then in my next step right down here, these h's can also cancel. So what's happening is I'm left with negative 3 over 3x times 3x plus h. At this point, I am ready to plug in my h of 0. I do it right here, and therefore I don't need to have this limit notation because I'm not telling you I'm going to take the limit, I'm actually taking the limit. So once I plug in the 0, I see that I basically have 3x times 3x, which is 3x squared, and my f prime of x, therefore, is negative 3 over 9 x squared. Now, could I reduce that? Of course. So I could have reduced that to negative 1, right, if I put 3 into both, over 3x squared. All right, and then this, once I have my generic slope, which is the f prime of x, to get f prime of 3, just go ahead and plug your 3 in for your x, and I get negative 3 over 81, which will also reduce to negative 1 over 27. Okay, so that was a second practice of how to do your limits when you have to get a common denominator. Okay, so now we're going to work with conjugate pairs with our last example of doing limits that involve algebraic manipulations. Just like in our other case a couple of pages ago when we had a radical and we were trying to figure out the limit and had to deal with radicals, the best approach is to use conjugate pairs, and we were able to cancel things out then. We're going to do the same thing here. So using conjugate pairs allows us to eliminate the radical, because when you square a radical you just get the same term without the radical symbol. And remember, our goal is to be able to cancel h's, and I can't cancel the h here because I can't get into the h there because it's underneath a radical symbol. So to eliminate my radicals, I'm going to form the conjugate pair. And remember from the previous pages, the conjugate pair just is exactly this term, exactly that term, and exactly that term. And since I had a subtraction here, I'm going to have an addition here. And I'm going to put it over itself. So this is the same term. Same over same is just a fancy 1, and that's why I'm allowed to do it. So just like before, if I recognize that I have a minus b, so if this is a and this is b, okay, times a plus b, so again, if you're terming this a and this b, then when I FOIL that, I will eventually get x squared minus b squared. Knowing that, and knowing that if I take radical 4 times x plus h and square it, I will just get 4 times x plus h. And let me work over here a little bit. So let me erase this one, and then look at our b. What is your b up here? So my b would be radical 4x. So if I take my radical 4x and I square that, that will just get me 4x. So that brings us to, let me just change color, to this step. And at this point, if I distribute in here, so let's see what I get. I'm going to erase this again, and we'll use my little side panel. So I'll just do some of that work up top. So I initially had this minus 4x. So if I distribute, I have this minus 4x. And what will happen is the 4x and the negative 4x will cancel out, which leaves me with positive 4h, which is what I have here. Then I still have, and I'm going to put this little, if I make this dark again, I'm going to put this little box here. So what I still have now is the same denominator I had over here, just written here with next to the h. And at this point, let's cancel out this h with that h, and I'm left getting ready now to actually take the limit. So wherever I had an h, which is right there, I'm plugging in a 0, and because I'm doing that, I'm no longer writing the limit as h goes to 0. Okay, so this is what I have, and now I'm going to say when h is 0, I really just have radical 4x plus another radical 4x, which just gives me 2 of them. I can then pull this 4 out, right? Because if I had this radical 4x, that is equivalent to radical 4 times radical x, and just taking the principal square root, that's going to be 2, and that's still going to be radical x. And since I had a 4 over there to begin with, right, because I really had this, so I have, is that right? No, excuse me, I had a 2 to begin with. 2, 2, so I have a 2 here. So 2 times 2 is 4, and that's where this 4 comes. You see 2 times the 2 I pulled out is 4. These 4's, so let me change colors again. These 4's can now cancel, and I'm left with f prime of x is 1 over radical x. They want us to evaluate this slope where x is 3, so I plug in a 3 wherever I have an x, and I get a slope of 1 over root 3, and you may leave it like that. So what is that slope? Just to clarify once again, if you were to draw a tangent line to the original function, which was f of x equals radical 4x, and you drew that tangent line where x was 3, you would have a slope of that tangent line of 1 over root 3. So that's what we're doing. Don't lose sight of that. So just to summarize, on day 2 of the 1.4 limits notes, what we did was we started out finding the limit as h goes to a number, and we learned 2 different algebraic manipulations. One was factoring and canceling, and one was using radicals and finding conjugate pairs. Then we moved back to finding the limit as h goes to 0 for the purposes of finding the first derivative. So our technique is to use your difference quotient. We had to do it in algebraic manipulation fashion, getting a common denominator, and also using conjugate pairs. So we've practiced the conjugate pair technique in 2 different places. So you may want to go back over and look at these notes and make sure they make sense to you, and use your notes to then try the homework for day 2.